Okay, so I want to generalize what we were talking about in the last video. So just as a reminder, this is what we had in the last video, and there were some intermediate computations that we weren't too sure about. They taken some inputs and which were the raw inputs, do some processing to them, and somehow this is supposed to give us a better idea of whether or not it's going to rain tomorrow. I want to generalize this. So let's say we have some inputs, x1, x2, and x3. And we have something that we're trying to predict, which is y. What we could do is we could do some hidden computations under the hood. Um, let's call this h1, and h2. And these are some computations or some intermediate computations that are happening as a sort of pre-processing step before we use the processed things, the processed knowledge, in order to predict what we want to know. And so these are actually sometimes called like input features. So like features, input. And this is the output, obviously. And as collectively, this could be called like an input, right? And here, these are sort of like hidden computations. So I'll write the word hidden. In other words, it could be like a hidden layer actually. So this is a intermediate computation that you do in before you get to the output. Or this is like the raw stuff, then you do an intermediate computation, and then you get your output. Or you could take it even further, which is like you could have three inputs, and then you could have two intermediate computations, and use those two intermediate computations to perform two other intermediate computations, and then you could use that to inform three other, or let's say four other intermediate computations, and then use those four highly processed features in order to give you your output, or like predict your output. So what's happening here is effectively I have layer zero. So this is like layer zero, and this is like a layer one, layer two, layer three, and then this is layer four, which is effectively the last layer. So sometimes actually what they do is they call this like lowercase l. That's a lowercase l, and then there's a three under that, and then they'll call this like capital L or something because it's like the last layer. Um, but you don't need to know about that right now. I guess what's going to happen is I'm going to use these three inputs to inform the computation for the stuff in layer one for this node, and then do it separately for this node, and then use these processed features in order to inform the computation for this node, and use this to inform the process for this node, and then use these two to compute for this and compute for this, and then so on and so forth. And you can use all of these four to give you your output or predict your output. And so you're probably thinking like this looks really complicated, but effectively what's happening is that you have your input, which is raw, and then you process it, and then you process it again. So it's like double processed and then triple processed, and then like your quadruple processed is hopefully your output. And so like it's a lot of processing going on. Like there's a lot of stuff that might be there that wasn't originally there in your raw data, and you might be able to actually make a lot of informed decisions or computations in this structure right here. And I guess you're probably asking what does this node represent? What does this node represent? And so over here, up here, I'd put, maybe we're calculating wind speed or we're calculating temperature. And then these things are allowing us to compute what the rain is, right? Whether or not there is rain. But um, more than that, I want to, I mean, I guess I want to point out to you that it doesn't have to be any specific thing. And in practice, when you're creating neural networks, and this is a neural network, when we're creating neural networks, we don't often know what do our intermediate computations or hidden computations, our hidden layers represent, right? So this is our input. This is our hidden layers, hidden layers. Um, we don't know what those nodes sort of represent, if they even represent anything, or if it's usually what happens is kind of it's too hard for a human to understand, or like it's too ambiguous for a human to understand. So we let the machine decide for itself what it wants those computations to be. And I know that's a really vague answer right now, but it'll make more sense once we start learning about gradient descent and what happens under the hood for all of these. And so I just wanted to bring to your attention one other thing, which is I created this neural network on the spot. I didn't prepare this beforehand, and that's because I can actually do a plug and play thing right here. There's three inputs, two intermediates in this layer, and two intermediates in this layer, and then four here, and then one here. We can create any sort of architecture that we would like to see over here, right? I could have put four here and then two here and two here, or I could put like 100 here, or I don't know. You can make any sort of combination that you want. And the idea of that is that basically neural networks can be of any shape, of any complexity. I could have had as many hidden layers as I want. And since they can be infinitely complex, what happens is that they can literally almost learn any function that there is to learn, whether it's for rain or detecting spam emails, detecting cancer. Basically, they can be extremely versatile. And technically speaking, you can use a neural network to learn any sort of function. But there are certain ways in which we can use neural networks that are better than others, which we'll be covering on later on. But yeah, so I guess since this is a pretty good introduction to like neural networks, I'll see you in the next video.